Hello, ladies and gentlemen. Today I'm going to talk about, Yellowstone National Park. Yellowstone National Park, in its most clear definition, is comparable to the human body in that it is a planetary aneurysm. Here's why. Alright, so I'm going to go right here. Here's why we have, well, actually, the title of this is supposed to be, because I haven't made the title yet, the title is supposed to be Yellowstone Grows. Here's why. Alright, I know I'm not really exciting person to listen to, but here you go, right? Now, the culprit behind Yellowstone coming into existence is the same culprit that is responsible for the North Pole slip. And when I say North Pole slip, I'm describing that when the impactor struck the Earth and it made this fracture loosen up all of its goo gaggets, the whole North Pole started to kind of have a meltdown. You see what I'm saying? So here's how it works, right? The top of the planet is the North Pole. The bottom of the planet is the South Pole. This is not because we put our globes on our desks with the South Pole facing the desktop. No. You have different forms of gravity. Around the planet you have the planet's gravitational force, which comes around the equator strongest. I know some scientists say it is stronger at the poles. I don't buy that. It's stronger at the equator. It's coming in and it basically forces things up and down. Notice my boop right there, right? Okay, it works the same pretty much in and out of every other aspect that you could possibly imagine. So here it is coming in like that. Then you have the solar gravity. So the sun has its gravitational influence. So if the Earth's gravity was stronger at the poles, the sun's gravity would be stronger at the poles. Then basically what that would mean is we would always be either on the North Pole or the South Pole around our ecliptic of the sun. That doesn't seem to be working that way. So yeah, I think maybe we could go ahead and stick with gravity stronger around the equator. Wouldn't you agree? Okay, I agree. So here's the thing, right? There's another gravitational force that affects our solar system and our planet, and that's galactic gravity. The galactic gravity is coming from SMEGAWs, supermassive electromagnetic gravity waves. That is the combination between two forces. You have supermassive electromagnetic supermass or SME buffers. Let me get this back down right. Supermassive electromagnetic braided field ropes. I like to call them ropes. Ropes because the ropes that come out of the sun are like coils and stuff like that. Well, that's kind of what we're getting when we get our waves from the apparent black hole, right? Or ropes. Okay, so they come around. That's like my other theory about the dragging the ropes. Why they have that spiraling thing going on. Okay, you have the SME buffers. And the SME buffers combine and join forces with the gravitational waves. So you end up with supermassive electromagnetic gravity waves. These waves are striking our planet from the base at the South Pole. So the gravitational force is greater here on Antarctica than it is on the North. Therefore, it's kind of like the base of my cup. Okay, so you could consider gravity from our Earth being like the gravity wave of our galaxy, smacking the bottom of the cup and making all that fluid in my cup hang out inside my cup. Alright, then you get the continental masses of marshmallows at the top at the North Pole, and then you get the hot chocolate and the sugar down here at the bottom, right? Alright, so we've discussed that. Okay, so the culprit, I'm going right back here. Here's our culprit, the South China Sea Impactor. It caused a terrible, terrible mess in our planet. And it made all of these waves come out from the North Pole. They all came from the North Pole, people. Why? Because they're flowing down. Okay, so they're flowing down and they're moving west. Well, that's mostly because our planet is rotating like this, okay? So they're going to go south toward the bottom of the planet and then travel west. Isn't that interesting how that works? Notice the similarity between this one here and that one there. That's a little bit different, but it also has to do with the way that the impactor struck this side of the planet, okay? Now, in the Nunavut Asthenospheric Tsunami coming down this way, guess what? You have a resident volcano, just like you do over here. I'm going to take it back over here to Siberia and all them places, right? Because it's Siberia, all those Siberians, man, they were just like letting the dirt loose, and it went down right down here into China. The Chinese were running. So here's what happens, right? It goes down here and flows, and it's under. Here's Eurasia, and then the asthenospheric tsunami, being the most viscous part of our inner Earth, is running underneath, and then it's trying to push its way up underneath that continent to boop, pop out of the continent. Like, see my finger? That's part of the continent there, and go boop right there out of the continent. It's not doing that, right? It's like, I can't do it. Oh, I ran out of energy. Beep. And my finger turned into the Himalayas. That's what happened, I'm trying to tell you, ladies and gentlemen. The world is not as solid as we might think. Okay. Now we figured out how in the world all of these waves of semi-molten lava ended up forming up over the top of the Pacific. It isn't because over the course of 4 trillion, billion, zillion, bajillion years, the Pacific is just going. It ain't doing that, folks. It's not that simple, right? Actually, it's quite a bit more simple. So Earth had a meltdown. Now, if you'll notice something here, because the South Pole is, in fact, the bottom of our planet, here's the reason that we're looking at pointed continents toward the base. In our clouds, every time we see clouds that have rain, nimbostratus, I'm primarily speaking of, right? You see little shady things coming down like that. That's rain coming down there like that, right? No, it's not always rain. Sometimes it's just a trailing little cloud at the base, and it kind of looks like the cloud has got like it's a bug, and its feet are just dragging behind it as it flies. That's called virga. All right. Well, when you're looking at South America and you see that it's large here at the north and pointed at the south, you look at Africa and it's extraordinarily large up here in the north and pointed at the south. You're looking at continental virga. And this whole area, all of the planet is basically migrating. The continents are migrating westward. Why are they migrating westward? Okay, this is why they're migrating westward, ladies and gentlemen. First of all, they're falling from the North Pole to the South Pole. Why? Because the continental mass was too great at the North Pole for the world to be able to maintain a balance. It is like the laundry machine from hell with a huge blanket in it going, so it's trying to fix itself, right? And that's what's happening. All that mass is starting to move out. Centrifugal force is making it go around down the outsides toward the center of the Earth at the equator, and it's trying to break loose. It's still marshmallows, and they're trying to move out, right? But eventually they're going to separate at the equator, and some is going to go to the south and some is going to go to the north to get that balance. Okay, and ultimately the Earth would be trying to get like a ocean that goes around the equator. We might never see this. And how do we know this? Just look at Jupiter. Come on. Do you see any vertical, lines on Jupiter? No, they're all horizontal lines. That's what planet Earth is trying to do with its continental masses. It's having a heck of a lot more trouble doing it because the continental masses and the Earth's crust is kind of hard and crackly and doesn't really want to cooperate. But it still comes up with virga. And this is what we have right here. Now, if I turn on my... there's a different reason we have virga in the shape of the North American continent, and here's why. Okay, I know that's another here's why, right? All right, so primary vortices, right back to that. You see that? North America falls right in between that temporal... I would call it a temporal zone, not because of temperature, but because of less activity, right? So it's kind of in the safe zone. So if the world ever becomes liquefied, this might be the safest place to be. Not down in here, though. That's kind of like where you're getting again. Oh, excuse me. You're going to get sucked up and spit out down here somewhere. All right, so, but is that really true? I don't know, because see, this vortex in the Pacific is going counterclockwise, which means it's going to, well, it'll take everybody who's flying around, getting a suntan over here in California and stuff, and just throw them back up here in the north. Okay, so California is not going to fall off into the ocean and go this way. California is going to separate. It's already apart here. You can see how it is. It's going to separate and go up this way toward the north and rotate around. That's just the way it is. All right. This one over here, the Sapaliwini vortex, of course, we can see the little woo, means we're rotating. It's also rotating counterclockwise. So you have two vortices rotating counterclockwise. And because they're both rotating counterclockwise, they have a turbulent tangent here. That's probably one of the places you don't want to be. All right, now we're going to go back. I'm going to take that off, okay? We've got the north and the south figured out. Here's why it's an aneurysm for up here. Well, I'm sorry, I'm going to go off to the side again here because we keep talking about this one over here. Now, you see, Taklamakan is a volcano, or at least it was, right? And this is like the Earth's Olympus Mons. It is the Earth's supermassive volcano. So we'll call it the Taklamakan supermassive volcano. It was a product of this landslide. This landslide came down, which really wasn't a landslide. It was actually carried by the asthenospheric tsunami traveling beneath it. And the tsunami rose at this point here, but could not penetrate the crust and made the mountain range of the Himalayas come up to the top and stop, okay, before it solidified. Then, because it couldn't go any farther, the Taklamakan supermassive volcano took over and started spewing out whatever was left that it could get rid of. And it goes up east, and notice that the lava flow from this volcano wasn't able to go very far this way, right? Now this is still when this particular vortex created by the impactor was quite busy and alive. So this material, this all happened very quickly, folks. This is not something that takes trillions of billions of zillions of years. This was immediate. And how immediate, I couldn't be certain, but immediate enough that you might actually be able to watch it from outer space. So this material is going and coming around this way and going blah, 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 and feeding into this vortex right here that's also going counterclockwise, which also partly affected the direction of the flow because this flow could not continue to go south here anyway. And so along with the force that makes our continents move and migrate westward, it continued to go this way westward. Okay, so now the other side, it flows out here. It flows across, creates a land bridge separating the Caspian Sea from this guy right here and that guy. This is the Arabian Sea, and this is the Persian Gulf right here. Okay, well, this all used to be connected, and then it goes over here just like one of those nightcaps. It comes out over here, pretty far. Yeah, it is. All right, now that we figured out that there's a volcano over there, now we're gonna come. Yes, volcano. Mr. Scientist who thinks I don't know the difference between a volcano and an impact crater. All right. Now, here we go. Over here you've got Yellowstone. Woo, right there, as a matter of fact, if you look at it, you got a little green side and you got the brown side. Yellowstone is it's a twin volcano, ladies and gentlemen. In this brown side, there's people living in that caldera. Yeah, it's not going to well, especially when we know that Yellowstone is growing. Here's why it's growing, though. So all this material moved down here. When that asthenospheric tsunami traveled down here, it's being pushed up against the lithosphere. And as it's going up against the lithosphere, where the crust has its anti-peaks poking down inside of the earth, it creates channels, it creates tunnels, just like Ape Cave on Mount St. Helens. Yeah, that's the right place. It creates these tubes and basically veins. And these veins have lava flow. So here's how it works. All of this material is getting sucked in like this and going boop. Well, what happens when it goes boop? Well, if it goes boop and it can't, thank you, Doodle. When it goes boop, and it has no place to go because there's a heart at you. That's right. It has. All right, stop, Doodle. You're confusing me. It can't go any farther, right? Because it's stuck by the crust. Well, it gets cycled back around. So it's doing this. It's coming in, going up, coming around, like that. And when it's coming around like that, guess what, people? It's feeding Yellowstone. So as all of this material just continues to feed Yellowstone, Yellowstone becomes bigger. It grows. It's an aneurysm. One of these days, it's going to burst. That's how it works. All right, I explained enough. Wow. I did that in record time. This is getting easier and easier. All right, so now that you have that figured out, all right, now for all the naysayers out there, ladies and gentlemen, this right here is a pop. I've got my cursor right on it. That's a pop. That is a point of penetration. This right here, yep, and it feeds into this fracture here, but this fracture here is actually one of the Jupiterian stripes, the most recent ones. That's why it's so clear. This Jupiterian stripe was affected and carved by this impactor. That's right. That's how it works. So it comes down here, goes like this. This is my birdie from badminton, right there, just like that. Now see how close these, I mean, by relation, or in relation to some of the other B2Ws, or blast bow waves that I've shown people in my videos. This one here is actually kind of tight. Now we got one going like this, goes like that. Now I'm not convinced that this is in particular a the Hawaiian, subterranean Hawaiian ridge here is in particular a B2W. It doesn't really appear to have the usual effects that you get with a B2W. But you notice, this is the one I refer to as the North Pacific Oceanic Impactor. This one was also a world-class impactor. It had to have been larger and bigger than this guy around here, because this one right here, I mean, look at the B2W on this guy. It just goes, it's a little tiny thing, go right there, and then boop, there's Spratly Islands right there in the freaking center of it. It's called the Pop, okay? And then you go and you look over here, and you're like, holy crap, that one was huge. In fact, it was so huge that if I was to try to determine any blast rings at all, it would never, even if the South China Sea Impactor did not cause all of this slippage from the North Pole, and this was still largely oceanic floor, it's well, the blast rings would have been well beyond 60 degrees, and that's when you start to get into global distortion. You're not going to really be able to tell the difference between a blast ring and just topographical features that begin to come into effect as you get closer toward the edge of the planet. So it's not very helpful. So now you know how this works, and now we know pretty much where the Rocky Mountains in this region came from. Okay. Now, there's quite a bit of a possibility that this right here is also another tsunami coming down here. In fact, I'm going to put my money on it. This one's separated here, and you have this broken up, icebergish looking crap up here in Nunavut coming down right down in here, and boop, you have another front for a wave. And a wave, all coming around down here toward the Pacific. Why? Because there's nothing there. That's why. And yeah, okay, now this is not the same thing. So centrifugal force is basically what pulls the continental virga down. And I got confused in some of my videos because I was convinced, and I didn't even recognize that I was contradicting myself. So, and in fact, I may have even contradicted myself in my book. I gotta go back and look at my books. I might have had this vortex going the wrong way. So it's going counterclockwise, right? So it's going against the direction that the continent pivoted. All right, so when the South China Sea Impactor struck, Africa and South America separated. Why did they separate? Because of centrifugal force pulling them down to the South Pole. It pulled them down, okay? And that's what caused that, right? And they're going down, they're vergiating toward the South Pole. Like, how do you like that, vergiating? I don't know, what do you call it? What do you say a virga is when it's that's an active virga, so it must be vergiating, right? Oh, well, whatever. Anyway, that's how our planet works. Pangaea never left us. Pangaea is still here, ladies and gentlemen. As a matter of fact, Russia is mostly Pangaea. And this little curly Q weird stuff going on right there in the Caspian Sea. Yeah, you know what? Bam! Right there, that little spit of land right there. That, ladies and gentlemen, was once the North Pole. All right, call me a crackpot or an essential crackpot. Yeah, who cares, right? I'm not a doctor. Doctors can be crackpots. I don't have to be a crackpot because I'm expected to be a crackpot. That's why I can't seem to get any scientists to listen to me. All right. That's pretty much it right there. I think I pretty well covered that. We went over that stuff. Now, if you notice over here, just as a quick note, since I have a little bit of time, not much, I don't have any time actually. Okay, so if I go back and I turn on where is it here? Vertical tectonics. No. It should be primary. Primary? Now I can't find it. Man, I tell you what. Oh, there it is, primary vortices. All right, there it is, folks, primary vortices. Okay, so if you notice the Sapaliwini vortex, which is rotating counterclockwise, well, check out where it's coming in. Right there on the other side of the I almost said the Aleutian Mountains, the Appalachian Mountains. And notice how they're all shaped like a wave right there. There's a lot going on right there, right? Oh my God! What is that? Oh, there's a little bump right there in the middle of the ocean. Oh, it looks like a circle going around it. Oh my God! It says it's Bermuda. Well, that's the Bermuda Ross there, folks. That's what I'm trying to tell you. That is your perfect, by criteria, impact site. And of course, yeah, no, you don't have anything going out here like we would expect to see, like we normally see on the moon. Earth, it doesn't work that way. This was a direct hit, ladies and gentlemen. There's your central peak. There's your central peak, and it was the Bermuda Rise impactor that was responsible for creating this wave of activity in the Appalachian Mountains. We got a lot of huge impactors around here, and Chicxulub ain't the biggest at all. Not even close. But it is bigger than people are mapping it. I've got that figured out too. All right, it was nice talking to you. I gotta go.